on quantum synchronization organized by the Department of Physics, Navadip Vidyasagar College. This is the fourth time in a row that we are organizing such a webinar. We are happy that we have managed to organize a webinar on quantum synchronization, which is currently a very hot topic in the field of research because it can show the way to build quantum computers. Google already announced that it has a quantum computer that is 100 million times faster than any classical computer in its lab. Our speaker will definitely elaborate this topic with more details to make it more clear, more exciting to you. Our college has made a lot of advances in the e-learning initiative. Along with the faculty, the support from our principal is a great factor too. After all, a ship is only as good as its captain. Now I want to request our principal sir, Dr. Sapun Kumar Roy, to deliver a welcome address. Principal sir, please.
Thank you, Dr. Nirmalendu Gonai. You have already heard that the title of the seminar is Quantum Synchronization. It is a national webinar and it is the fourth time. That is, the Department of Physics has already completed 3 webinars. Today, if you include today, that is the fourth. Number of webinars will be 4. So it is the achievement of the Department of Physics, Navadip Vidyasagar College. We have with us our honorable speaker, respected speaker, eminent speaker, Dr. Soikat Ghosh, who is an associate professor and attached to Department of Physics, IIT Kanpur. We are very much thankful to him because he has actually responded to our call in haste. Whenever we have sent an invitation letter to him, he has responded to our call. We are very much happy that he has accepted this proposal, this invitation. Thank you, Dr. Soikat Ghosh. Perhaps your speech, your valuable speech, will enrich the students, the participants who have already joined this webinar. Thank you, Dr. Soikat Ghosh, for being with us. Next, I want to congratulate Dr. Prabhas Mondal, who is the departmental head of the of physics, and he is also the convener of this webinar, Quantum Synchronization. Organizing secretary, Dr. Nirmalendu Gonai, he is a very much enthusiastic teacher. He handles everything. I do not undermine the other members of this faculty, but he plays a very key role, particularly in organizing or arranging such type of seminar or webinar. Other members who are also genius, that is the James, Professor Ashim Kumar Bishas, Professor Rajkumar Mondal, Professor Nidarshana Guho, Professor Sudipta Modak. All are very good teachers, teachers of the Department of Physics. I express my thanks and gratitude to the members of the organizing committee, Ashim Kumar Bishas, Professor Rajkumar Mondal, Nidarshana Guho, and Professor Sudipta Modak. And as the seminar is going to be held in collaboration with the IQAC, and that is the jointly IQAC and Department of Physics are organizing this webinar. So I congratulate my Dr. Bhaskar Chatterjee, who is the coordinator of IQAC. We always get his support in this regard. And the technical support, that is the main issue. That is the success depends on the execution of a webinar in a smooth way, depends on the technical assistance. So Dr. Nirmalendu Gonai and Professor Sudipta Modak are playing this role, are playing a very predominant role in this regard. So thank you, Dr. Nirmalendu Gonai and Professor Sudipta Modak. Our President, Sri Biman Krishna Saha, Governing Body President, Biman Krishna Saha, he is the source of our inspiration. He is our inspiration. He always wants to see our college as a college which is academically development, technologically development, that is overall development. He wants to see overall development. So I thank you, sir, Biman Krishna Saha. The participants, I hope, I am sure that you will be enlightened, enriched by the valuable, by the precious speech of Dr. Soikat Ghosh, who is from the Department of Physics, IIT Kanpur. Again, I thank you, Dr. Soikat Ghosh, for accepting our invitation and for being with us to speak on quantum synchronization. Thank you all. Thank you. Over to Dr. Nirmalendu Ganai.
Yeah, thank you, sir. Now I request Dr. Prabhas Mondol, Head of the Department of Physics, Navadvip Vidyasagar College, to say something about our webinar. Prabhas, please.
Good afternoon, everybody. First of all, I welcome all the participants of this national webinar. I express my deep sense of gratitude and thanks to our respected Principal, Dr. Swapan Kumar Roy, the distinguished and honorable speaker, Dr. Soikat Ghosh, Associate Professor, Department of Physics, Kanpur IIT, all the respected professors and teachers of different colleges and schools, research scholars and students for their participation on this digital platform. This is our consecutive fourth webinar over the last 1 month and a half. This time, huge number of more than 600 participants have registered, and that is why we are really grateful to them. The theme of today's webinar is quantum synchronization. It is the study of synchronicity by quantum physics. In short, non-causal synchronization can be observed in independent subatomic particles. The quantum synchronization has a great role in quantum computers and quantum communication devices. Our esteemed speaker will explain the theme elaborately to the audience. Now, the direct teaching learning method has come to a standstill after the outbreak of COVID-19 all over the world over the last several months. That is why we have arranged this digital seminar to encourage the students during this crisis time so that they can pursue research in this new and emerging field afterwards. We sincerely hope that both the teachers and the students community will be enriched by the valuable speech of the speaker. We are really grateful to our honorable speaker for giving his consent to talk in this webinar. I express my heartfelt thanks and gratitude to him for this. My special thanks to our college Professor Nidarshana Guho, who corresponded with our respected speaker for this webinar. Lastly, I express my thanks and gratitude to our respected principal, Dr. Swapan Kumar Roy, the coordinator of IQAC of our college, Dr. Bhaskar Chatterjee, to all my departmental colleagues, Dr. Ashim Kumar Biswas, Professor Rajkumar Mondol, Dr. Nirmalendu Ganai, and Mr. Sudipto Modok for their encouragement and active participation in this digital seminar. Special thanks due to Dr. Nirmalendu Ganai and Mr. Sudipto Modok, who have played the key role in organizing this seminar. Very much thanks to them. Thanks to all of you. Very much thanks to our respected speaker. Thank you, sir.
Yeah, thank you, Pravasda. All the participants are requested to mute their microphones, keep their video off, and not to share their screen throughout the webinar. If you have any relevant question, then please unmute your microphone first and ask the question directly to the speaker. Our speaker will be very happy to interact with you directly. You can also post your relevant questions in the chat box. In that case, you will get an answer to your question from the speaker after the lecture. It is my pleasure to introduce our speaker, Dr. Soikat Ghosh. Soikat Ghosh is an associate professor of physics at IIT Kanpur. He completed BSc Honors in Physics from Presidency College, Kolkata, MSc from IIT Bombay, and PhD from Cornell University, New York. Following postdoctoral research work at MIT and Cornell University, he joined IIT Kanpur in 2012. His research work includes quantum optics, atomic and molecular physics, laser-cooled cold atom, and nanophotonics. Now it is the time to request our honorable speaker, Dr. Soikat Ghosh, to start today's lecture. Sir, please start.
Me? Hello? Can you hear me?
Yes.
Can you hear me with this microphone?
Yes, yes. Perfect.
Huh? Can you hear me now?
Yeah, we can hear you. Yeah, perfect.
Microphone, my headphone is not working.
Yeah, maybe. So you can share your slide. Yeah.
Yeah. Before the. Yeah, can you see my slide? Hello?
Yeah. Yeah, we can see. We can see. Yeah,
Yeah.
perfect. Yeah.
Okay, so let me just start. But before that, a real great thanks to giving this chance, to opportunity to actually interact, to Nidarshana for getting in touch first, and then now today it was really heartening to hear the words of Professor Roy, Professor Mondal, Professor Garin. Like these are a really great opportunity. It would have been much nicer to actually being able to visit. Hello?
Yeah.
Can you? Yeah, okay. So actually the problem with the full screen mode is that I really cannot see anything. So if sometimes it stops, I might not know. So I might sometimes ask whether things are fine. Yeah, so thanks a lot for this opportunity. So particularly it's kind of exciting because, I'll be talking about a problem whose parts and bits we have been working for 8 long years. Actually, we are an experimental group in IIT Kanpur. We work on this emerging field of quantum technologies. So actually, these experiments are very hard. One needs to build their own instruments, and it takes a long time. It takes a great patience. In IIT Kanpur, actually, that was very nice that the undergraduate students, the very enthusiastic PhD students and master students, all of them came together to build this lab with the 8 years of work. And we have been studying few things, but recently we had a result which we are very, very excited about. The paper just came out, in fact, last month, 1st of July. And it's being very well received. So just to summarize in one opening slide what I'll be talking about, synchronization, a phenomena which is very, very widely observed in nature, except that we might not have heard of it, or we might not have been aware of it, so we don't know it. But synchronization, this is a picture on the can everyone see my cursor as I move my cursor?
Yes, yes.
Okay, let me just get a. Is this slightly better?
Yeah.
Yeah. So this is a picture. Actually, it's a spectacular picture of fireflies. Jonaki. Flashing in the forest. And in certain species of fireflies, this flashing of independent fireflies synchronize, and you see the whole forest kind of light up together and turn on and off. It's like a Diwali lighting, and this kind of things occurs everywhere. Even like the reason the heart, all the muscles they pump together in a rhythm is because of synchronization. It happens in electrical grid lines. It happens probably in our brains, in our neural networks, and so on. So this is a phenomena which over last 20-30 years, a lot of physicists have been speculating that whether similar synchronization that we see all the time in this our world, that is the classical world, can that happen also in the quantum world? You know, by quantum world, I'll come in details what I mean by quantum world, but I basically mean atoms and, you know, molecules and electrons and things that behave quantum mechanically. So can those objects also synchronize? And we are the first lab in the world, you may say, who actually experimentally observed this quantum synchronization. That's the paper I'm talking of, which just came out. And in fact, American Physical Society already kind of accepts it. They actually wrote a whole news article on our work saying that this is the first observation of quantum synchronization. And that's really, in a very simple layman's language, is what I'll be talking about. So I have a lot to cover, but I'll do that in simple way. But that doesn't mean that the physics is simple. I'll be hiding many of the details under the carpet, but if you have questions, please, you know, either interrupt. I'll not have a way to see, in fact, your chat box questions. So you may actually just send it to the coordinator of the talk, or, you know, just maybe turn on your microphone. I don't know. Like, but you feel free to ask questions. So basically, if I divide the talk in two halves, one half is that, you know, like two completely very otherwise different things. One is something that as students we are just starting to learn, maybe in college, quantum mechanics, or we might be experts here sitting in the audience. So one half of the talk is on quantum mechanics, you know, what is quantum mechanics in very brief sense, the essence of it, and why that is so important today, you know, as Professor Roy, when he was introducing quantum synchronization, was saying that, you know, in quantum computers, why this is important. So these are like very few slides of just kind of to encourage students to think of this field and possibly, you know, work on this. It's a very exciting time to work on this, with many open questions. The other half is basically classical, which is synchronization. I'll assume that many of the audience here never heard of the word synchronization. You know, in Bengali it's called Shomoloy or Shomoloyon, you know, like in the same beat. Synchronize, but I'll actually give a very brief introduction to that phenomenon. And then at the end, depending on the time, I'll talk about what we have done and what we have observed. So I'll start with the quantum world, which is basically a very, very strange and interesting world. So the figure you are seeing here is actually a scale, a logarithmic scale, in fact, of length, and you can see that it's a meter scale. So humans are somewhere about a few meters, you know, or a meter or so. You know, that's at the 10 to the power 0. You know, so Mount Everest is somewhere like 10 to the power 4 or so meters. You know, and so on and so forth. You're going. This is the larger distance. Quantum mechanics usually, not always, but we find quantum behavior when we go to the other limit, which is basically the smaller and smaller length scales. You know, like roughly the length scales where humans can actually make features by hand, like not by hand, by machines. You know, the nano scale, nanometer scale. You know, in fact, the Pentium chip in our laptops and computers, they are starting to have like 14 nanometer, 20 nanometer kind of features, or 10 nanometer even. You know, so from that scale onwards, as you go downwards, you see mostly these particles behave in a way which is not classical, which is basically something completely a different world, like really bizarre. It's this quantum world. And that's kind of what is observed. You know, there are many unknown questions that, in fact, you know, people don't know where this transition happens, you know, classical, quantum to classical, and so on. But roughly, this is what has been observed. There are also other cases, like in case of optics or light, you know, there as such the length scale doesn't make sense, size of a photon, you know, but there one finds that as you make the light weaker and weaker and weaker, at some point when it's very, very weak, you start seeing it's behaving as if it's a quantum mechanical object. And what is this quantum mechanics? You know, like what is the essential essence of this quantum behavior? If you see, this is what we learned when we start the first course of quantum mechanics. In between, we do a lot of like linear algebra and a lot of complexity, a lot of integration, and so on. At the end, also, we come back to the utter bizarreness of what we learned in the beginning, which is basically the fact that things are waves and things interfere, like, so we know, like, this is a picture of, like, kind of two drops, icicles falling on water, and you see this fine waves kind of starting to produce, and you also see that the two kind of crests of the waves where they meet, there are regions where there is like constructive interference and destructive interference. There is something we are familiar. We have seen these things, interfere like on a string or on a spring, on different things. Waves we understand, but we really don't understand. And when these waves, we are told that, as you go to smaller and smaller objects, you take those objects, they have mass, they are like particles, but they actually behave like waves. When we are told this, we don't understand. At the end also, we don't understand what is this wave. These are these waves, and we are also told that, these are actually probability waves. So what do I mean by that? So this is a little small bit of maths. It's basically, people have done these experiments. I'll show the data. So you are doing an experiment where you are basically throwing like streams of electrons, through a hole. So out of the hole, the electrons are coming out, and then a little further you have two slits, like two holes, so that actually as the electrons are coming out, it can go through this hole or that hole. And then at a later time, so you put a screen. So this is a double slit assembly. You put a screen and you observe what you see. So normally our intuition will say that the electrons either like go through this hole or that hole. So with time, you will basically have a distribution where either the distribution is either centered around the first hole or the second hole. So basically they are probabilistic. That's what we expect for like throwing sand or throwing billiard balls. So there will be double hump, just two of these. But actually and factually, when you actually go and do the experiment in the lab, what you find is that there's a wave. So it's actually, this is how it looks like, as if what has gone through the holes are these two states of electrons, such that the electron as if is like a wave which has gone through both the holes at the same time. So it is in some sort of a abstract state. You can imagine these are like little vectors, state going through. Here is S1 and S2. So it's a superposition of these both possibilities, S1 plus S2. And what we are told is that what we see in real life is the square of the superposition. So some sort of a dot product of this vector, S1 dot S1 or S1 dot S2 dot S2. So that's what we see, and very interestingly, that what the dot product is telling us is saying that it's a probability wave. That's the most bizarre part of it, that as if each of these electrons are part of a probability wave, it kind of knows where to fall on. And overall, if you do it with many electrons, you will see it. So this is how a true experiment. This was actually voted as the most beautiful experiment of last century. It was done by this, one of this top Japanese Mitsubishi or IBM maybe did this experiment. Where they basically threw this, actually literally did this double slit experiment, and this is what they saw. Initially, this is a picture of the screen, and as the electron falls on the screen, it creates a white pattern dot. So that's an electron detector. So when one electron falls on the screen, you can see where it fallen. So whether it's like a wave or it's like a particle, you can see that. So you start with a blank screen, and after a little while, you see basically that there are little white dots, on the screen. You run it a little longer, you see like electrons are falling as if randomly, nothing spectacular. You would say, see, I told you, like, it's random. But as you go on more and more, this is after a long time when many electrons are fallen, you actually see that it's not that there are two spots, white spots here and there. That would have been like just electrons going to this slit or that slit. But as if every electron kind of knew where to go through, because overall, when you have repeated, there's a wave-like structure. And this is kind of the strangest mystery, that in these particles we are forced to think of them as carrying these probability waves. Einstein making this statement here, like he never liked this probabilistic interpretation, and here he's saying this is in 1943, so this is already pretty late, and he's kind of angrily saying that, as I have said so many times, God doesn't play dice with the world. So this probabilistic interpretation of this wave function is just not true. correct, whereas more and more and more experiments have shown that this is accurately, very, very accurate and very exact description of at least what the world we see, and here Stephen Hawking is taking a jab at Einstein, saying that not only does God play dice, that not only that the quantum world is probabilistic, but it also, he sometimes throws them in places where we cannot see, so basically he's kind of hinting towards extra dimensions that, those might also be real, like there might be dimensions that we cannot see. So, but anyways, the superposition, the wave property, that the wave can go simultaneously through this and that, through two states, is something, so mysteriously bizarre that, it has created a lot of like different scenarios. So two scenarios I'll talk about. One is a very bizarre scenario where there's due to Schrödinger, one of the fathers of quantum mechanics, he's basically, created this scenario, which is famously called the Schrödinger cat paradox. So just imagine, a situation where you have a big box and you have put a live cat inside the box, and you have a cyanide, like someone actually made this arrangement where there's a cyanide bottle and there's a hammer, and this hammer has a little trigger arrangement, so that if at subatomic, if there's a decay, if there's a radioactive decay happens, some quantum particle comes out, triggers an electronic circuit, which basically makes this hammer go duck, and it breaks the cyanide bottle. The cyanide comes out, the cat dies. So that is the scenario, and the box is closed. So normally, if you're asked, so is the cat dead or alive? Our normal senses will say that the cat is, I don't know, of course, I need to see whether the cat is dead or alive, but the cat is either dead or alive, but it's either dead or alive, but quantum mechanics tells you that no, it's actually, this is another state you can think of nature, which is actually observed to be true, is that the cat is alive and dead at the same time. It's a different thing, like as if there are two cats and they are live vectors. The state alive is a vector and the state dead is a vector, and it is actually, as long as you have not seen it, it is in a superposition of dead and alive at the same time. You are the one, when you open the box to see the cat, you actually find it dead. If you find it dead, you are the one who killed it, because the act of observing is what collapsed this superposed state of the dead and the alive cat at the same time, to be dead. So this is, Schrödinger was saying that, see, this is a paradox, but it cannot happen. The cat is either dead or alive, so something is wrong. But actually, it turns out people have still not done the experiment with a real cat, but there are these things now called Schrödinger's cat state. In fact, the state I have written below is a Schrödinger's cat state, which are basically very macroscopic states, can be in two states. Just imagine a ferromagnet, with all spins up and all spins down. So if you actually create a state which is a million spins up plus a million spins down, that would be a Schrödinger's cat state, and people have done very close to those kind of experiments. So actually, it turns out that you can actually see these very macroscopic objects in such states. There's another very interesting superposition. So this is an example I keep giving to my students when I teach optics, that if you, for example, take a glass rod and send in a laser pointer, let's say, so you will see something like this on the screen. There's a kind of green bright light, going through, and that's it basically. But and you will usually say that, oh, see, I can see the light in the glass. But if you actually look very, very closely, what you're seeing is not really the free light, but it's light interacting with the glass atoms, and the atoms are being jiggled, and in turn they actually irradiate back. Hello? Hello?
We can hear you. You can just continue.
Okay. Yeah. So the atoms can radiate back. So the way we will learn it in BSc physics is that there's the electric field of the electromagnetic field, the light E is not E anymore, but it's D, because now it is the electric field plus the reaction of the atoms. right? So now if you actually go deeper and deeper into it, at some point the atoms become quantum mechanical for you. You will start imagining atoms as like so that these are not just like classical billiard balls. The light becomes quantum mechanical for you. You can actually treat the light pulse that's going through as a quantum mechanical object. And what you find is that
Hello, sir. Your slide is not visible.
my slide is not visible.
Yes, slide is visible. Please pin the presentation thing.
Okay, just 1 second.
No, you are okay. I think.
No, it was visible actually. It was visible. We could just see that.
I stopped it.
Clearly.
Yeah, you stopped. I think now you stopped. You have stopped.
I'll Is it visible now?
Uh,
No,
yeah.
no, no.
Yes.
Now it's
yes.
visible.
Yes. Now
Yes,
it's
it is
fine.
visible.
Yes,
Is
it's fine.
there anyone for whom it's not visible? No.
Yes, it's visible.
Okay, great. Yeah. So basically, you see, like if you zoom in inside this glass, you will basically find the states actually are not either atom or photons, but they are kind of a combined state. This is kind of a baby way I try to what happened? Yeah, write it, so a part of it is light or photonic, a part of it is atomic, and it goes into a superposition of an atom plus photon. And in fact, that superposition is a very mathematical superposition. You can actually change this phi and change this cosine alpha and sine beta component. So there are scenarios where what you can do is this laser light which is going through the glass, you can actually tune the properties cosine alpha and sine beta, and initially have a light pulse, and then make cosine alpha 0, sine beta 1, and then make it an atomic state, and then later make sine beta 0 and cosine alpha 1, and that again makes it a light pulse. So you can actually take a light pulse, which is like traveling at 3×10⁸ meters per second, the fastest moving object. It goes inside this glassy material like atoms, interacts with atoms. You do something, you can actually make it completely atomic. So you actually store the information inside the atom, so basically you store a light pulse and then release it back. So you see that presently, as I talk also, this informations are being digitized and sent through actually these cables, data cables, which are just, optical fibers. They're basically just chopped light pulses going through. And now this kind of techniques, I'll talk about these experiments we do in the lab, where actually you can take such a light pulse and convert it into an atomic excitation. It's exactly like the cat being dead and alive. In this case, the cat alive is the light pulse, cat dead is kind of the atoms. You convert it back and then convert the atom back, so make the dead cat alive, kind of. So this kind of things, are very interesting, very paradoxical. That's why quantum world is bizarre. But nevertheless, now it's actually becoming economically very important, because of the fact that you see here, like, the CEO of probably the world's biggest company now, Google, Sundar Pichai, is standing inside this physics lab in front of a very complex instrument and posing. This was last year, like Google claimed this quantum supremacy, which is basically what they did is they made a computer where actually internally you use these properties of these atoms and this superposition in a way to do computation such that, it can be much, much, much faster than what you can do with a supercomputer. The best computers in the world, and one way of thinking about this is the following, that all computation, like this is just one slide introduction to quantum computer, that all computation is actually, if you see, classical computation is done with binary digits, so 0 and 1, on and off states, so just two states, this orange and blue, 0 and 1. Whereas a quantum computer, if you give this two states 0 and 1, it will not only have 0 or 1, but it will also have all possible superpositions of 0 and 1. So cosine alpha 0 plus e to the power I phi sine beta 1. So basically you see that this superposition is like a vector. So in fact, it can show that it actually, like this vector, depending on how you change the angles, can actually span on the surface of a sphere, and every point on that sphere, exactly like your two poles, north and south, the 0 and 1, every point is also a piece of information. So just if you can just make a single quantum bit, which is called a qubit, that itself becomes very powerful. If you can imagine that, like all computation are done by this basic two-state, 2 points, and so one bit of information, basically 0 to 1. And here you have so many on the surface of the sphere. So a qubit itself is very powerful. And just imagine, bringing 50 of them on 60 of them. That 60 qubit quantum computer is what Google made, and that is faster than any of the presently, doing one particular task is faster than the best computer by days. But there's another very interesting aspect. I'll not go much into that. That actually is what all the governments very interested, because quantum mechanics, also because of its very interesting theorem called no cloning theorem, it actually promises 100% secure communication. Quantum mechanics, there's a very simple way of looking at this very simple theorem which tells you that you cannot make copies of a quantum state. So you have a piece of paper, you want to steal it. So what one would do, you got a question paper, so you would basically make copies of it and leave the original in the professor's desk and take the question paper. But here, if the question paper was an atom, basically, if you try to make a copy, you basically destroy the atom. And in the process, you really cannot make copies without the person knowing it. And suppose this atom was a key to a particular secret message, the moment I see that my key is damaged because someone tried to make a copy, I'll throw the key and make another key. So as a result, it kind of gives you 100% security. And this is a picture from the 2017, 16th June in Science cover, where China, for the first time, demonstrated in a very, very, very crude way, in a very inefficient way, but nevertheless showed that they can send quantum states of light to the satellite and receive it back. And that basically said that China is making this secure communication network, and you can imagine its consequence in defense, for example, where the security is the most important thing. So the whole world went into this quantum race now. This year, for finance minister in the Indian Parliament promised 8,000, 9,000 crores almost for building quantum technology. So it's a great time to actually get into this field. So to summarize up to this point, what we have talked about is we have zoomed down to this very low scales, and talked a little bit about this quantum properties, this possibility, like the fact that massive particles, things with mass, actually superpose with massless objects or with itself, different states, gives this tremendous computation and communication powers. But there are many, many unknown questions also. For example, there are no one really knows, as I was saying, that this dotted line I have put where the boundary is. This is a completely open question that I am saying nanometers, but why nanometers? Are you going to see quantum effects in micrometer scale? People have seen that. Are you going to see it like larger scales, like man-made objects? People have seen quantum effects. Trillions of atoms, people have seen quantum effects. So where is the transition from the quantum world to the classical world? Where do you draw this dotted line? No one really knows. Similarly, there are speculations that some quantum objects like this cosmic strings, in the early universe might have gotten so big that they might be at the scales, this very, very large, extremely large scales, and one might actually see it astrophysically. There are many, 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 many interesting questions around this, but nevertheless, it's also being used in technologies. So that's kind of I think exactly I took half an hour. That's the one half of the story, which many of you already knew probably, which is quantum mechanics and quantum technologies. Very simple introduction. Now I'll move to the other half of the talk, which is a much more like observable thing and fun thing of synchronization. So synchronization is a topic which relates to first and foremost natural oscillators, things that are oscillating and randomly oscillating. For example, you have noticed that after a talk or a concert, people start clapping. And if you notice carefully, after a while, the clap gets synchronized. That actually happens not because people are intentionally trying to synchronize, but it's a very weak coupling of natural oscillations that's actually doing that. So this is a picture of fireflies. I'll come to fireflies. I have some nice videos to show after this. So electrical engineers, for example, know a lot about synchronization because there is the synchronization of power grid lines. 50 hertz or 60 hertz can synchronize and can lead to catastrophic damage. Like suddenly like things can break apart, large amounts of vibrational energy at a particular frequency. So they need to be very careful about this. Windmills, actually they put them in a line to synchronize. They actually aid each other and kind of create some better efficient power designs. As I was saying, muscles in our body are actually synchronized natural oscillators, and so probably is our brain and even our sense of perceptions and memory, like long-term memory and so on. There might be synchronization going on. So it's a field which is very widely, starting from basic physics to biology to engineering to medicine, very widely studied physics. And it actually started very interestingly. First time it was systematically observed comparatively recently in 1665 by Christian Huygens, polymath, an expert in many fields, fathers of many fields. So he would come back from his lab and research, whatever, and every night he would sleep in his room, and there were these two big pendulum clocks. And one thing he would notice, he being a curious mind, a scientist of the greatest caliber, notice that no matter how the clocks he start, remember these clocks are at that time probably they had mechanical springs that will continue their pendulum motion. Or presently the clocks are actually with batteries, so that is what is called. So they're natural oscillators, they'll continue their oscillation. But after a while, these two completely independent clocks, their pendulums would synchronize, and they'll start oscillating together. So Huygens, would write these letters to his father that what is it, maybe the air molecules are talking, maybe the walls. So he gets the walls, there's some vibrations that must be transferring from one to the other and coupling. So he would put them further and further apart. So actually he found that they took longer to synchronize. So slowly he did this famous, in 1665 he basically did this famous experiment where he took a piece of wood and hung two of these pendulums and showed that this wood is the weak coupling which actually synchronizes these two things. So let me just show you here. Hello? Hello?
Yes.
Yes, sir.
Yes,
So I'm
everything
sure
is okay.
my slides are visible.
Yes, everything is.
Yeah. So I'm just trying to, let me see if this comes in. Okay. So I'll basically show first a modern day version of Huygens. Please, if someone can confirm if you can hear the volume. So what you will be seeing are what are called metronomes. So these things you can buy from hobby stores. These are like little pendulums, and you can actually set the frequency. So you are seeing here 5 metronomes. So they have an internal battery which is tuck, 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 it's going like that. So there are 5 metronomes slightly at different frequencies. So initially they are like oscillating at the, and I don't know if the sound will come in, you will hear this noise and they're kind of random scattered. But after, like what this person will do, he's basically doing the Huygens experiment. So he will put it on a wood and put the wood on this kind of connected bridge, which is placed on this little improvised wheels, Coke bottles, and you will see that as these things are moving, the bridge gets coupled, so it starts shaking like that, and slowly the whole thing starts synchronizing. So I'll just play this video. If someone can confirm this one. Can you hear the
Yes.
sound?
Yes, yes.
Yes, we can hear you.
Okay, I'll just stop. Could you hear the sound getting into synchrony? It's like a Ravi Shankar's Zakir Hussain concert. At the end, the clapping is getting synchronous. These are like non-living objects. They have their own internal mechanism. Their frequencies are slightly different. But all of them got into synchrony. And if you actually noticed carefully, you saw the bridge kind of moving back and forth. Like as they were getting into synchrony. So that's what I'll show you. It's a real life example now that in 2000, the London actually made this Millennium Bridge, which was a gem of a design, made by some greatest architects of all times, and implemented by some great engineers. This is a bridge like the second Hooghly Bridge of Calcutta, but actually the suspension is on the side, not on the top. The usual thing, so it was made with great accuracy. It's a walking bridge, footbridge, but on the day in 2000 when it opened, I'll show you a video next of this. You will notice carefully. What happened was, as a lot of people came, Millennium 2000, 1st Jan, I think, or people came to walk, and as they started walking, they felt that the bridge is wobbly. So they were all like shaking, and the bridge was really moving. And it was a mystery for all the engineers and the architects that, they simulated the whole thing, calculated there should not have been this movement. Much later, after seeing the videos in a year or two, experts in synchronization showed that it was a strange case of synchronization, but the humans were like the metronomes. Each of them felt that, oh, the bridge is wobbling a little. So they, started like walking in a particular pattern. And though that synchronization actually made the bridge wobble. So I'll show you this video. There's a raw footage from top of the bridge. You will see that people are so scared. This is on the first day when it opened in 2000, a video from then. People are so scared that some are holding onto the bridge because they're thinking the bridge is going to fall. And as the video will zoom out, watch carefully, you will see all people are walking in a funny fashion, as if there's a mass synchronization. None of them know. All of them are walking because they're thinking the bridge is wobbly. And because they're walking like that, that is what makes the bridge wobbly. so that's kind of the strange thing about synchronization. Sorry. So see, as it will start panning out, you can already see people walking in a sync. But now watch, Okay, I'll stop here. You can watch and read more about it. It's a very, a lot has been written on it. What happened to my? Yes, but that's kind of the thing, that it actually shows that the synchronization, whenever there's a weak coupling, it will happen. And it doesn't require humans to be intelligent to get synchronized in clappings, or even for Mexican waves in stadiums. And similarly, it's exactly like the yeah.
Sir,
Yeah.
in the case of the bridge, does the natural frequency of bridge is similar to the frequency of the man who are walking through the bridge? Does this type of thing happen?
Yeah, so there is a there are frequencies, but you see now normally people will not walk like that. If you go back and see the video, people are walking out strangely. In fact, there are longer videos of this. If you watch, like they're interviewing people and they're all saying they're walking sideways. So you see like a bridge complex structure in a many. Hello? Hello?
Yes, sir, please continue. Please continue.
Yeah, so just to answer, like a bridge like that, you have many natural frequencies, fundamentals and higher order modes. It will have longitudinal, transverse, and so on. So that as an engineer or an architect, you design a bridge so that the dominant modes are damped out, and those little tiny sideways modes are so small vibrations that unless something spectacular is happening, those will not get excited. In this case, they got excited because of the synchronous people. That's basically. So this is the transverse mode that got excited. Yeah, I cannot hear. Hello.
I'm requesting the organizers to just mute the talking around. We cannot hear him.
Yeah, there's some other voice coming in. Okay,
So you can continue now.
Yeah, I'll give another example. My most favorite example. In fact, the work that we did can be understood from this example. So these are examples of fireflies, Jonaki basically. So these fireflies are, like spectacular things. We have all seen them growing up. Certain species of fireflies, actually, they are also natural oscillators. They're glowing. But certain species, somehow they start syncing with each other. And soon you see an entire forest in the dark, like turning on and off. I'll show a video of that. And it's a spectacular thing actually, like completely like a lightning show going on. Let me just show this video actually.
A synchronous firefly ranges throughout the southern Appalachians. It really is a pretty magical thing to see. I think people are just fascinated by fireflies, and especially growing up. A lot of people have experiences of catching fireflies in stars, looking at how they're doing their flashing. Maybe it reminds them of their youth, and they want to bring their children out to experience. The synchronous firefly can be distinguished from other species by its pattern of 6 flashes about half a second apart. It may look somewhat random at first, but when you get a high density of males flashing, the synchronicity of the dark period is very obvious, and then the flashing itself as the night goes on.
Okay, yeah. So you saw, I think, towards the end, the synchronicity. The dark period starts getting longer, and then suddenly they light up. Yeah. So that's basically something you can go and see. But so just to come now, so these are like some examples. Just to come to the basic essence of what these different examples of synchronizing they have. They are basically the thing that is common in them is what is technically called a limit cycle oscillator. So this is a little undergraduate harmonic oscillator physics that if you are solving harmonic oscillator problems, you see that basically you can plot them in a position and momentum space, and a particular oscillator state is basically a point there, a vector, which is basically saying that it has a position and momentum, and it has a particular phase, that phase is basically phi. So it's basically saying that your x-axis is going as a cosine omega t, and y-axis is going as a b sine omega t. If a equals b, it will be like a cycle. So all of these cases that you saw, this harmonic oscillator, this people walking, metronomes, grandfather clocks on the wall, all of them are harmonic oscillators. They are basically, except that they do not have a well-defined phase. They have an amplitude. So they are inherently, technically, what would be called nonlinear oscillators. There's a gain mechanism and there's a loss mechanism. They kind of cancel each other to reach an amplitude, but there's no phase. So they actually form literally a cycle in this A-B plane, or the quadrature plane. So there is no well-defined phase. And what is happening is that as these things are oscillating, if it gets a little phase perturbation, I'm just saying this technically, so that if people who are technically interested will understand it right away. So if there's a little phase perturbation, the system, which otherwise didn't have a phase, just goes and locks to that particular phase, and that's kind of can happen in a chain, in a series, so for example, so basically, like these are the different cases that can happen. So synchronization always requires this limit cycle oscillator, something that's actually going on and on and on, because internally it has a loss mechanism and a gain mechanism, and they kind of balance to a particular amplitude. So you can actually synchronize this limit cycle oscillator to a particular external forcing. So for example, for Huygens pendulums, you can, if you go and periodically tap on the wall at regular intervals, after a while you will see your pendulum will actually start locking to your tapping if you're doing it consistently. So there can be like many such couplings, like like the way you saw the fireflies, like all these limit cycle oscillators coupling. But this might also be satellites on orbit, and all of them actually can couple in to form what we would call a satellite communication network. So that's also synchronizing the satellites. Two of them coupling. There's a very interesting regime which is also important for communication and satellite technology. That there can be a master-slave configuration where there's a central one, the master, and that actually slaves all the others, and all of them start following. So that's actually a very interesting configuration. Let me again show you another. This is, I promise, the last video. Where people try to do this actually in real life. These fireflies, they're sinking. So as humans, we are like free, control free. So some people ask the question that suppose I take a LED light and fool the fireflies to think that it's a firefly, and we flash that LED. Now the fireflies see each other's flashing, and that's how they get adjusted. That's a weak coupling. That's kind of this weak raw connection between them. In case of LED, there is no coupling, so the LED will continue flashing like that. Can the fireflies synchronize? So that's, and this is the last video, and there's a reason why I'm showing this videos, because it will help talk about what we did. So you'll see a single LED which is made out of electronics. That's the forcing which is flashing. That's the master. And the firefly stupidly synchronized to it. That's the LED. You see a firefly next to it is synchronized. Yeah, now the whole forest is synchronizing. See? Yeah, so let me stop here. You see that this is like what classically one is doing, that you actually have an external forcing, and you're asking, can all these different fireflies blinking actually can synchronize? This is exactly very similar to the experiment that I'll be describing now. Now I come after, this is the kind of the ending of the introduction to synchronization. So now the question is, if I take these fireflies and replace them by tiny little atoms, and prepare the atoms in a state so that they are like limit cycle oscillators. They are like, just getting a firefly is not enough. No, you need to make the firefly blink. So you need to actually have the oscillation. So if I actually take these atoms, prepare them in a state so that they are actually limit cycle oscillators, whatever that means in quantum mechanically, can they synchronize to a LED, as in like, instead of an LED, suppose I send some quantum coupling, can this little atoms synchronize to that? That's really the question that we tried to answer. This was a question which was around for a while, that, can you observe synchronization in the, how long do I have?
Yeah, you can if you need the time.
Yeah, I'll take another 10 minutes or so.
Yeah, that's fine, no problem.
Yeah. So just to say, sometimes people get confused that if I take an oscillator and if I start forcing it, of course with the force, the oscillator is, if I solve harmonic oscillator problem with f cosine omega t solving, of course the solution is x cosine omega t, so it's in phase with forcing. The only difference is the following, that for a harmonic oscillator, suppose you give a small little perturbation, it's a little coupling with the neighbor, it will have a perturbation, but when the perturbation dies out, it will settle down to its original phase, the function of time. Whereas a limit cycle oscillator, if you give a small little perturbation, it picks up that phase and continues with that phase. This is really the physics behind synchronization, that many such limit cycle oscillators can just pick up each other's perturbation and just synchronize. So basically this is the question that we asked, that can quantum objects like atoms or spins synchronize to external forcing and to each other? So now a very quick tour of this 8 years of experiment setup that I was talking about. So first you need these fireflies. So we use atoms, and these atoms normally, if you see at room temperature also, like we are constantly hit by atoms moving at 300 meters per second, 350 meters per second. That's what we call temperature. In this case, we actually, inside a vacuum chamber, we use laser lights and hit these atoms, some chosen atoms with light, and they scatter. They absorb, emits this light in isotropic direction, deals a momentum recoil. If you do that enough, eventually you can take these atoms from 300 meters per second and pull them down to millimeters per second. So they're literally like, condensed in front of you, and their temperature as a result, because they're so much colder, their temperature is very low, and eventually if you can do it right, you can go to very, very close to absolute zero. So this is the temperature we reach routinely in our lab. This is the machine, how it looks like. Everything is homemade. There are magnetic coils and traps, but we reach temperatures like 50 microkelvin. So very, very close to absolute zero. And this is, if you come to the lab, this is what you will see literally naked eye. These are pictures taken with cameras or webcams. This is a cloud. What you're looking at is actually, it looks like a cloud of about 1 million atoms. So just imagine Avogadro's number is like 10 to the 24 atoms. So this 10 to the 6 atoms. So extremely dilute atoms, they're scattering of photons, and that's why they look loud. They're like little dust particles, and this is the coldest thing you can ever see, really low temperature, and you can play very interesting games. You can literally like make like jalebi-like shapes with these atoms. This is actually a trap which is made like a donut, and the atoms are moving, almost crawling at like millimeters per second around this donut. So this is the starting point. This is like catching the fireflies in the lab, and this is a long process, but let me just leave it there. This is a cartoon of the experiment. These are the cloud of atoms, this rugby-shaped object, and then we send in different laser lights. And simple way of saying it is, these different laser lights are like the LED, except that now the LED is much more complex. So this is, as I was saying, just getting the fireflies is not enough. You need to make them to blink. So similarly for the atoms, this is very technical. You need to prepare them in a very specific spin state. So there's a spin 1 atoms, and you need to prepare them in the middle of the spin state, which corresponds to a limit cycle. If you actually visualize the state in phase space, it exactly looks like a limit cycle. So effectively, atoms are not harmonic oscillators, spins are not oscillators, but in phase space, their state looks like that of limit cycles. So now is the question of turning on the LEDs, and this is the place. This goes back earlier when I was giving these examples of Schrodinger cat, quantum mechanics. This little tutorial I took, so there was a part where I talked about light and glass. You remember, or light or atoms interacting, and I was saying that if you look very closely, actually the light interacts coherently with the atom, and you can actually make a light go into an atom, and we do. So so this is how a typical experiment looks like. So imagine this is a light pulse. We call it omega p for some reason. So a light pulse falls on a photodetector. It's a pulse of light. So in time you will see this pulse. This is the starting point. There's nothing else there. Now we trap these atoms and put this cloud in the path. So now what you see is this red line, which is basically no light is now falling on the detector because you have put something which is blocking the path, and so the atoms are basically scattering of the photons, and so nothing. You see basically the light pulse has become very small. Now something else you can do. That's just complexity. You can turn on another field perpendicular to this direction, and if its frequency and everything is right, you actually get back. So this was the all absorbed light. Now you can get back this entire light, but what is coming out is in the superposition of atoms and photons, and that's the experiment I wanted to show you. That if you, for example, as this is coming out, at some point if you turn it off, it gets absorbed back again. But when it's absorbed, it's actually absorbed coherently in the atoms, exactly like that cat becoming dead and then coming back alive. Like that, the light you have converted into atoms, and proof is that later time when you turn back on this other light in a perpendicular direction, you get back this light. So it actually goes into a very exotic superposition of partially this optical field, partially the atoms. These little things you can control how much of it will be atoms and photons. So this is a quantum, what I call quantum memories of light. You can store light inside atoms, and this has been a field of study for last 15 years or 20 years. A very active field of study. So that's kind of this thing I was talking about earlier, and that's what the main thing we use. So so now this is just so you can imagine that the storing of light inside the atom. So when the atom actually stores the light is the LED. So if you think of the atoms as the fireflies, we are trying to synchronize the fireflies, and this light pulse that gets stored. So this is the raw data. This is how it looks like, magnetic field. So these are actually in this region. This is the light pulse coming in and getting stored in this region. It's actually all atomic, and then later you turn it back on at different times, and you get back that light which was stored in. So basically, this entire process is like the LED. To simplify it, so that is the little flashing light to which all the atoms synchronize, and there are very definite signatures of that. Maybe I'm almost running out of time. I'll just skip that. It's just not this simple, but there are signatures. People have been predicting. You can actually construct measures of synchronization. There's a process thing called synchronization blockade. Though synchronization happens always in classical system, but in quantum mechanics, energy is exchanged as packets of energy or quantas of energy. So there are regions where it cannot exchange a packet, and so there's a destructive interference, and that actually blocks the synchronization. So that's basically what we have observed also. And finally, just to throw this term, people who are very familiar with synchronization and nonlinear dynamics probably knows about this, that there's a telltale, there's a what I call smoking gun signature, like as in like the real proof that it is observation is there's a particular shape called Arnold's tongue. And we actually saw the emergence of Arnold's tongue very clearly in a measure of synchronization, actually. So with that, I'll just stop. So all I'll say is that we saw the equivalent of synchronizing 1 million atoms or 1 million fireflies to a LED. We saw the synchronization, similar things with atoms which are picked from picked in a vacuum chamber, cooled down to very close to absolute zero, and then light is stored in them, and in that stored light state we find that they get synchronized to the light, except that you see that for a firefly and the LED, you saw in the video there is the LED and there was a firefly standing. They are like different objects, but in this case the quantum state is actually a superposition of the firefly and the LED, and at some point the LED becomes the firefly, all of it, and then you take it back to LED. Like, it's no matter how strange it sounds like, that's the classical interpretation of this experiment. So finally, the question: can quantum objects like atoms or spin synchronize to external forcing? The answer is yes. They can. That's what we found. It kind of so it just came out. You can see published 1st of July in Physical Review Letters. It was also chosen as the editor's suggestion, as one of their featured research. In this journal called Physics. There's a nice article written by Christopher Crockett on our work, where they actually say very clearly that thus demonstrating quantum synchronization for the first time. So they already in American Physical Society accepts that this is the first demonstration ever of quantum synchronization. There's a very nice article in Quint. If you want, I can send it in the chat box, the link of that, written by this author and writer Dilip D'Souza on our work. It's a very long article, and everything I said, he talks in much more beautifully and nicely our work on this. So you can also look at that. So with that, I should say that the students are everything they did. Primarily Arif. He is actually from this Agra, Nungi area, Calcutta. So this was his PhD work. Part of it is like 1/3 of his PhD work was this problem. And then Pratik, next to him, Shupradip. But the others also, we do kind of interesting things with graphene and so. I'm ready to take questions if there's any. Thank you. Thanks a lot for attending this.
Yeah, thank you, sir, for your beautiful lecture, and congratulations for your paper in PRL. Yeah, now we can take a question from the audience if they have some. Okay, let me check the text box. Yeah, there is a question from Dr. Soumen Ghosh. The question is, how does the spin quantum number responsible for the quantum synchronization? Is the entanglement a normal sequence of quantum synchronization?
Yeah, so both are very good questions. So let me just, I'll also send here.
You can also check, yeah.
All the one article based on this work to all, yeah. So, yeah, so the first question is basically kind of the key question. So just to give you the history of quantum synchronization for last 20-30 years, there were theorists who were speculating that can quantum systems also synchronize. So one thing they were trying to do was actually to, theoretically, to actually take a nonlinear van der Pol oscillator and quantize it and see quantum behaviors there. And that is what was going on. And the experiments were very hard to do, to see like really quantum, with quantum harmonic oscillators. So in 2018, actually, this group in Switzerland, they for the first time started asking that, can you really see synchronization with something which has no classical analog at all? So spin systems, So if you think of it, spin system doesn't have position or momentum. So it's not at all like a harmonic oscillator system. It's purely spin degrees of freedom. And so there, what do we mean by limit cycle? So it actually more of a question of symmetry of the limit cycle, and then exactly a state in the phase space getting localized. And what they found is that firstly, like for spin half, the smallest possible quantum system is spin half. You actually cannot synchronize because of the strange property of spin half that any Hamiltonian kind of sets the symmetry axis. So there cannot be a state independently of the Hamiltonian applied, which is symmetric across an axis, except unless the state lies on the axis, and that's not a limit cycle. So their PRL became famous because of the fact that they gave a no-go theorem that that spin qubits cannot be synchronized. Quantum system that can be synchronized is a spin 1 system, and that's the experiment we do. And from there on, you can show that spin 1 and higher spin systems can synchronize. So I don't know if that answers the question, but basically there's a no-go for spin half, and higher systems one should be able to synchronize. So that is the first question, and the second question was what was the second question?
Is the entanglement a normal?
Yeah, so that's actually a big open question, So the same guys, Roulet and Bruder, they actually in 2018, later in that year, they published another PRL where they show that there's a very intimate connection between entanglement and synchronization. Or people have argued this way or that way. So for example, in our lab just before the lockdown, those are the experiments we are doing. We are basically trying to see that we now see synchronization and the synchronization measure in the atomic system. Is there a connection between this and the state superposition or entanglement or quantum correlations? Like for example, you can actually get these atoms emit photons and you can measure G2. The quantum measurement, like from where you can calculate entanglement. So is that connected to synchronization? These are very open questions. Like, this is kind of like starting from 2018, this field started. So it's very new and things are very open yet, so. Yeah.
Next question from D. Manas Mohit, asking that, are the fireflies coupled through air, or is there some other mechanism?
They observe each other, so they see. So you see that there is always a coupling. So fireflies actually, as they are blinking, they also see each other. So there is a visual coupling, right? So, so for example, people who are into this automated flight, like I really like that field because of that feedback and control theory. So they make these little drones. And you can see like beautiful TED Talks on this, tiny little drones, and you can like have 50 of them, and they synchronize. That's studying that the synchronization is also a very interesting field. But they actually take feedback from each other, so they are actually like imaging each other and using that data and their position they synchronize. So it's like that. So just like when people in clapping synchronize, they actually hear each other's voice, but you don't need to think. That's the whole point. Like the fact that there's a little coupling eventually will add you up into a synchronous state.
Yeah. Next question is from Vishnu K. Nambiar. Some bird groups follow a spectacular array in their movement. Is that an example similar?
Yeah. In fact, I should have. I thought that a picture or video speaks 1,000 words than me speaking, particularly in this time. So in this talk, I used a lot of videos. In fact, that is a video I really wanted to use, and many thanks for bringing that point out. So in fact, that's a spectacular demonstration. The bird flocking. Particularly, you will see that there are these videos of birds being chased by a large predator. Predatory bird. So or little bats coming out and being chased by an eagle. And you will see beautiful patterns. This you see also among fish swarms. Swarms of fish, and then a shark is trying to catch in between. So you see this beautiful pattern formation, and actually you see that they are not really planning this, choreographing this whole dance, but all they are trying to do is the nearest neighbor. They are trying to keep close to nearest neighbor and at the same time avoid the main predator, and that's how they synchronize. Yeah. So I don't know. You might say that synchronization by itself is an emergent phenomena. So it's tiny little rules, and even you find synchronization often.
Can we, next question from Chanchal Mandal, can we assume the quantum synchronization as an outcome of some entanglement in quantum mechanical level?
We don't know that yet. That's open question, yeah. So entanglement is one phenomena, synchronization is another phenomena. So, yeah, it's not clear, but one thing is that, entanglement, if you see, is also a fancier, two-mode effect, minimum two-mode effect of the main quantum effect, which is again superposition. So AB plus BA, that's kind of an entangled state, but the plus is the most important thing. So quantum mechanics inherently has the superposition effects, and we find that superposition plays a critical role in quantum synchronization. Like this synchronization blockade that I was talking about, there's a regime, but you cannot synchronize things because their waves destructively interfere. And this is an effect you don't see in classical synchronization. People have never seen that.
Yeah. Next question from Arindam Pramani. In case of qubit, is it the limit cycle oscillation that plays the role of synchronization?
So for a qubit, that's the main issue, that there is no limit cycle oscillation. So it cannot be synchronized. So, like you can only synchronize, limit cycles. So something which is circular, or cyclic, are the things which are synchronizing. So synchronization is necessarily a dynamical concept. You cannot say, oh, like 2-3 things which are like standing still, can they synchronize? No, like, or something that is flowing, 2 taps of water flowing, can they synchronize? There is no meaning to say. Synchronization is about periodicity, like the beats getting synchronized. And so, yeah, so yeah, I don't know if that answers the question.
Yeah. Next question from Partho Sarkar. What is the application of quantum computing in medical science to make treatment of cancer? Actually, medical science. Yeah.
Yeah, I don't know. I don't know that. Yeah, honestly, like yeah, I don't know. So there is a field, emerging field, which is called quantum biology, where actually people are realizing that birds, for example, the way they navigate through air, like they make cross-continent travel, there are still nanomagnets, and that has quantum mechanics. Or photosynthesis has quantum mechanical superposition playing an important role. But I don't know of any usage yet of quantum mechanics and cancer. I don't know. Because you see, like cancer is at a level of genes. That's what I'm saying. That like much larger scales, like micron scales. So there you don't expect quantum mechanics. Maybe in cancer, maybe these genes flip, and maybe that process. I don't know really anything about biology, so I'm talking outside my territory. But maybe that flipping, of the genes, like the base pairs randomly, that might have a quantum mechanical effect. Maybe if you understand it at that level, you might be able to stop it. I don't know. I'm saying random things probably, but I really don't know directly quantum computer how that's going to solve problems of cancer or COVID, coronavirus, for example.
Yeah. Next question from Kajal Krishnode. If we can control the emission of electron such that electron comes out at a time, what will happen in double slit experiment? I think.
Well, that's kind of, see, like one thing to realize is that, like there are issues of having very well structured, like one by one electron. But suppose you can, that every electron comes out at a fixed time, you have made a source, you will see exactly what I showed you. Because that's kind of this famous, what I call Dirac's interpretation, regarding this electron or a photon. You can do it with single photons one at a time also. You will basically find, the thing is that every electron interferes with itself, or every photon interferes with itself. That's what Dirac would say. The interference is happening not because multiple electrons are coming in, but every electron interferes with itself. Though finally you see a little dot somewhere there on the screen, a single dot for a single electron, but it somehow contains the nature of information. This has been tested very well, and that's kind of the essence of quantum mechanics. It's not because many electrons are falling. You can take one electron, like throw it there, you'll see it going somewhere, reaching somewhere. If you can collect it back, throw it again, and keep doing that, you'll see again it forms. Eventually, it's like flipping coins.
Okay. Next question from Muskan Sao. Sir, in the double slit experiment using electron beams, you said the electron somehow knew where they were supposed to fall on the screen. So what is the reason?
Well, that is not a right statement. Yeah, I don't mean to say that they knew where to fall on the screen, and it's not right for me to use the word "knew" because particularly beginning phases in physics, there is a tendency of thinking, oh, what is there in electron's mind? It's basically by that statement I wanted to say that every electron is carrying a probability wave. So it's falling. It seems like it has fallen randomly, but it has fallen randomly as part of a bigger picture. As in, like if that electron didn't interact with the silver particle on the glass film, and if you could have collected it back, that's what I'm trying to say. And if you throw it again, you will see it fall another place, and you do that experiment like 100 times, and you will see that everywhere it has fallen actually constitutes that pattern. Right, so that's what I mean when I say that it knew, except that of course it doesn't know the way, it doesn't have a mind, or there's nothing spooky or fancy going on. It's just that it carries this probability wave. So like the particle is at the same time going through the two slits. So yeah, it's very bizarre, but it's.
Yeah. Next question from Subham Srimani. The question is, randomness increases with entropy. Is there any relation between randomness and synchronization?
Well, yeah. So the question is basically, so synchronization can be there in classical systems, and there is a question that is there a connection between synchronization and randomness, and that has been studied. Synchronization, this particular limit cycle has a stability. If you start adding noise, eventually it becomes unstable and so on. In case of quantum mechanics, it is kind of like randomness means many things in quantum mechanics, but effectively randomness and what we call dissipation or decoherence, they are very intimately connected. And very bizarrely in synchronization, we find that if you increase decay or decoherence, which is another side of the coin of the randomness, you actually synchronize better. It's a very strange thing, but it's like what we find is that, and this was predicted actually, synchronization is better driven by decay processes or decoherence. But I should also say that the way we understand randomness in classical systems and the randomness that I'm talking of for this electron falling or the probabilities in quantum system, that randomness seems to be very inherent. It's as if like this quantum randomness there's no reason to understand randomness there. And I'm saying that randomness and decay are very connected. I have some fluctuation, dissipation, Einstein reduction in mind. So I have a model of a randomness. But in quantum mechanics, actually the randomness is inherent. Like there's no, like we don't know where this randomness comes from in quantum mechanics.
Next question from Kajal Krishnode. If we can control the emission of electrons such that single electron comes out at a time, what will happen in the double slit experiment?
It's similar, yeah. That's what I'm saying. You will exactly see the same thing. You can do it just with one electron. You can. You'll soon see the same thing. It's the same question that was asked before. It has nothing to do with many electron coming. It's a single particle phenomenon.
Okay. Application of quantum synchronization. Someone is asking. Application of quantum synchronization.
Yeah, I don't know. We don't yet work in application, but there are already very well-established fields. One is what is called quantum networks. Like very similar to our present internet networks. You have satellites and they exchange photons. Very early field. China showed some results. So there actually synchronization can play a very important role. There's another field which is of my interest personally. It's measurements. It turns out that I can ask this very simple question that I have given a piece of. Hello. Yeah, so you can take a piece of wood and you can ask how accurately I can measure. So when you're asking this question, you find that to measure more and more accurately, you need more and more finer scales. Because you're trying to see the edge where it falls. And as you go more and more, you are reaching at some point so small scales to see the matching, and you find that everything is jagged, and like there's no such sharp boundary. So statistical description, probabilistic description, and you can ask that, is there a fundamental limit of how well I can know properties of a system? This is what is called the quantum measurement problem. How well can I measure? If I say I want to measure the frequency of this thing, or if I want to measure the length of this or mass of this, are there fundamental limitations? Or the question is, if I have the most accurate instrument, I can always measure with the highest possible precision. It turns out that the second statement is not true. There are fundamental physical limitations of how well we can measure. And it turns out that processes of synchronization and so on can really aid in that process. So that's what is called the field of quantum metrology, like, how on measurements, on accurate measurements. And that's something which can be a very, very important application. How well you can measure time, for example. And synchronization might help there. So that's something we are very interested in.
Okay, thank you, sir. So there is no more question. So we want to inform all the participants that a link of the feedback form will be sent to your registered email address today. After the submission of your valuable feedback, you will receive your e-certificate of participation through your registered email. Thanks to all of you for your active participation in the webinar. Hope that all of you enjoyed the webinar and enriched yourself. I want to thank Dr. Soikat Ghosh for his splendid lecture, and we are grateful that he has accepted our request and agreed to deliver a web lecture. I also want to thank our principal sir and coordinator IQAP for their active support. Last but not least, I want to thank all of my colleagues for their continuous help and cooperation. Thank you and goodbye. See you soon. Yeah, thank you, sir.
Thank you.
Yeah, thank you, sir, for your valuable speech.
Thanks a lot. Thanks a lot to everyone for being here.
Okay, bye.